Okay, I'm going to pick up where I left off in the last video with one small change. At the end I said w prime of t is equal to negative 0.254, and that should be w prime of v. So this is kind of a strange function and derivative. Usually we do things in terms of time, but here we're doing it in terms of velocity of the wind, which is in miles per hour. So I have the derivative here, and I need to find a graph for that. So if I just went over and used the same window that I had previously, you can see that the derivative doesn't really even show up on there. And I'm looking for something at negative 0.254, which is very small. It may be that it's the graph, the scale of the y values or of the w values is so large that I can't even see the function here. So I'm going to shrink that by quite a bit. So I go to window, I'm going to leave the v values still going from 5 to 60, and I'm going to change the y values to go from, let's try negative 1 just to positive 1 by ones, and see if that makes any difference there. Alright, so I can actually see the function showing up there. And I'm looking for where this is equal to negative 0.254, and the easiest way to do that is to go in and add a third function down, and that would be negative 0.254, and look for where those graphs intersect. So I'm going to do second calc, use intersect this time, first curve, yes, second curve. Since there's only one point of intersection, I just guess, hit enter and for the guess, and it will find it at 22.989. And so that should answer this question. We've found the value of v, which is 22.989, at which the instantaneous rate of change of w, which is w prime of t, which I've graphed here, is equal to the average rate of change of w, which is negative 0.254, and so we're all set there. For part C, over the time interval from t to goes from 0 to 4 hours, the air temperature is a constant 32 degrees. Then at time t equals 0, the wind velocity is v equals 20 miles per hour. And if the wind velocity increases at a constant rate of 5 miles per hour, what is the rate of change of the wind chill with respect to time at t equals 3 hours? And indicate units of measure. So this statement is very convoluted, and we'll have to unwind it a bit. One thing that might help is to try to identify what is it that we're looking for in the end. That may direct us as to what we need to set up. So what we're looking for is the rate of change of the wind chill with respect to time at time t equals 3 hours. So if you recall that wind chill is w of v, or we'll just say w here, and we're looking for the rate of change of w with respect to time. So I think it's fair to say that what we're looking for is dw dt, and what we're going to need to do is to take the derivative of w with respect to time. And it almost seems like a kind of related rates problem here. So if we have w is equal to 55.6 minus 22.1, and so if you recall, and I want to try to do this without getting while using the calculator, but I may not be able to. So let's state it this way. If w is equal to 55.6 minus 22.1 v to the 0.16, and I want to take the derivative of both sides with respect to time, so the 55 is going to zero out, and negative 22.1 is a constant multiple, so we use the constant multiple rule, and the derivative of an exponential is, sorry, but that's not exponential, it's just a to the 0.16 power. And the way we'll do that is bring down the 0.16, then we want to reduce 0.16 by 1, and remember in the end to multiply by dv dt, like so. We'll simplify a bit, and that gives us something like negative 3.536 v to the negative 0.84 dv dt. And we're told that the wind velocity increases at a constant rate of 5 miles per hour, so dv dt is really 5. And I'm going to continue this in the next video.